Hello, my dear friends. In last video, we left off here where we could construct our graph and see how the neighbors and the different edges were interacting. So now we would start from here, and we would actually implement the Dijkstra's algorithm in our C and C++ setup. So first of all, before we dive into that function, let's remove that. We don't need that. And here we need two functions, basically two utility functions. One is we need to find the nodes uh, with the label. So let me write that function quickly. Uh, find node index. This function will be helpful to us whenever we pass uh, a string of a node label. We should be able to get its index in the graph. So we need this function, and it would be helpful for us. And here we will pass a string node label. And let me quickly implement this function. This node label function we need this functions because when we are actually implementing this, then there will be a use case where we have to we won't be able to specify the particular index. We only have labels, so we have to find the index properly. So let's quickly implement this function. This is a very simple function. We have to just initialize the index by -1. Uh, -1 actually gives us a status as well. If we didn't find that node label, we would know that this node label was wrong. And similarly, we would see if the nodes are empty, then we would return this -1. If they are not empty and we find the label, then we return that index. Otherwise, it would still return negative. So this is one utility function. The second utility function is we also have to uh, find the we also have to find the edge index. If we want to if we give starting node index and destination node index, then we should be able to find uh, the edge index. So we need that function as well. It would be helpful for us. So okay, in this function we are passing source node index and destination node index, and we this is very similar. If the edges are empty, then we just return -1. If we have edges, then we have to look for two things. First of all, one-to-one mapping of edges source node with source node index with our given source node index, and at the same time the destination node index of the edge should match the destination node index provided by us. But as we know that the graph is bidirectional, it means that if there is an edge from A to B, then there is also an edge from B to A. So we have to check the reverse case as well. We have to check that the source node index is matching with the destination node index, and the destination node index is matching with source node index. This will ensure that we get an edge if an edge exists between these two nodes. Then, in order to implement Dijkstra correctly, as we saw in previous video, we also have to have minimum distance neighbor. So for that, we quickly add that function as well. So here we would get an array, a vector of different indexes. Then we would check those indexes. So here we would, and we have to also know, understand, we have to also have to get the minimum distance for all the given indexes. So we would need this because we in our step 4 of Dijkstra algorithm, we stated that we have to choose the next neighbor. The next neighbor is based on the shortest distance from the current node to the shortest distance neighbor. We have to find that here. So we would be given these indexes of nodes, and we would just simply iterate over these nodes and we would get their distance, and whichever distance we would update the minimum distance. Once this loop is done, we would get that node with the minimum possible distance. So we are updating the index, and this index is what we need. So this is our third utility function. There is also one more function which we need for now. Uh, this function would be used to check for duplicates. So uh, we need this function because when we are going to implement the Dijkstra algorithm, we would see that there would be an uh, array of unvisited nodes. So if we want to add a new node to that array, we have to make sure that it's not a duplicate, because many nodes can have same neighbors. So if we are exploring a particular uh, node and its neighbor is suppose A, then maybe after some iterations there is another node whose neighbor is A also. So we don't need to add A more than once in our unvisited nodes. So this function simply returns the status if the index we are talking about is duplicate or not. So with these functions, we are set to implement our Dijkstra algorithm. So for that, uh, let's uh, uh, let's see what we need. So we don't have any return type for Dijkstra. So Dijkstra algorithm would need this function would need a graph. Obviously, we need a graph, and then we need source node index, and we also need destination node index. And let's quickly write down the steps that are needed to complete this um, function. So here I'm just going to add the steps. So these are our steps. First of all, we have to make a vector of unvisited nodes. So let's make that vector. So it would be vector of integer, and we would call it unvisited node. Then our source node, which we have here, we will just mark it we would just mark this distance as 0, graph the check nodes, and we would pass in source node index, and we would also set distance to 0, because the source node would have always have the distance of 0. So we would also need to add this node index into our vector. So we would just simply add unvisited nodes dot pushback this source node index. And here we also would want to copy this index, current source node index, into because we are going to write a while loop, and we would update this index consistently in every iteration. So we would need it. We don't want to mess with this index because it would be helpful later. I would explain why. So we would write a while loop while unvisited nodes are not empty. So we'll reverse this condition, and then we would start writing our while loop. So here is our while loop. So we will make sure that okay. So first of all, we would make sure that we run a for loop for all the currently neighbors of the current node. So here we would write a for loop. So here we would write a for loop to iterate over all the neighbors of this current node. So let me quickly write that. graph get nodes, and we would pass in the current source node index, and then we would add get neighbors dot size, and this would give us all the neighbors of currently the source node which is in our unvisited array. So we would iterate over it, and so now we have to make sure that this neighbor is not marked. So first of all, let's make our life easier and write the um, let's pick this index out. This neighbor, we let's copy this and make our lives easier. And let's write that neighbor index is equal to this expression. Then we would give it I. So this would give us a current neighbor. Now we have to make sure that this node is not visited. We would only update the distances of the nodes which are not visited. So we would write this if graph dot get nodes dot neighbor index dot get is visited. If this is false, only then we have to update this. So we write this, and so we would update it here. Mm, Okay, so let's quickly do update this. So we have to update the distance. So first of all, we would write the current distance of this node. What is the current distance? It's very simple. We would just okay. So in order to get current distance, we have to find the edge. So let's get edge index, and we have already written the function. So we would just call that function find edge index, and we need to pass graph. Then we need to pass current source node index, which is our source, and neighbor index. So this neighbor index we would pass in this function. Then for the current index, we just have to go to graph dot get edges, and then we would pass this edge index. So and our current distance is okay. So not current distance, but this would be cost. Let me and the cost. This will be cost. So we can get the edge cost. Okay. Let me explain that. So first of all, we would need current distance. The current distance would be simple. It would be coming from that node, get nodes, then this neighbor index, and that get distance. So this would give us distance of that the current distance. Then we have to have the approaching distance, which would be from the source node. So let me quickly copy and just add the correct index here. Mm, And here we would just like this. So this is approaching distance, and we, as we saw that our formula was to find the minimum of current distance and approaching distance plus cost. So current, so let me find appropriate name. So let's say new distance is equal to minimum of current distance and approaching distance plus cost. So this is our expression. We are writing it directly as it is. And now we would update this distance, but can only update it if the new distance is less than. If the new distance is less than current distance. If it is less, then we have to do two things. We have to update the distance of the neighbor index. Yes, so we have to update this set distance to new distance. This is step one. Then we also have to update the parent. So we would just dot set parent node index. It would become current source node index. So this is how we would update the parents of this node, and we would add this distance. Now we have to do one more step. We have to add this node to unvisited uh, array, unvisited vector. So for that, our next function would be helpful, which is duplicate function. If uh, check duplicate, we would pass the unvisited nodes, and we would pass this neighbor neighborhood index. If this one is not duplicate, only then add this to unvisited nodes to not unvisited nodes vector. So we will have neighbor index. So this is how we are going to iterate over each and every neighbor, and then we would add this neighbor correctly in our unvisited nodes. Now, what we have to do, we have to mark this node as visited. So it would be very simple. We have to just mark this current source index node as visited. So we would just mark this as set visited to be true. So we have marked this as visited. Now we have to remove this node from the unvisited nodes. So we have a very nice combination of two functions which help us do this. So uh, we have to write this. We have to write unvisited nodes dot arrays, and then we have to pass chain that function with remove for. So what this line does is this remove function basically takes this current this element, and it takes it to the end of the vector. Then this arrays function removes that from the end of the vector. So these two in combination, when these two functions are used in combination, they remove the uh, that element from the vector. So for that to work properly, we also have to include algorithm, library called algorithm. So now it would work as desired. So let's get back here, and now we have to choose the next node to become the source node. This is an important step, and we know that we have to find the minimum distance neighbor. So to be safe, we have to create a variable called new index, and we will call find minimum distance neighbor. We would pass in graph, then we would pass in this unvisited nodes array in here. And if we get a new index as -1, it means that either it means that all the either visited nodes are empty, or it means that we cannot reach to any other node. So it means we have to uh, finish this processing. Our Dijkstra is complete. And if it's not the case, then we just have to update current source node index to the new node. So we would just visited nodes and unvisited nodes, and we would give this new index. So it would make sure that from visited unvisited nodes, we choose that index which has minimum possible distance. And now we would also add another terminating condition, which is if the current source node index is equal to destination node index, we don't have to process any further. We have to break the loop. So this is our Dijkstra. So we have to with this we have completed our all the steps of the Dijkstra algorithm. So we can actually check that. So in order to check that, we have to here our Dijkstra is finished. So when we run this, we can actually see how we can actually see that if it has found the path or not. So we would just simply write a very nice message here. So suppose uh, let me quickly try to write a message. So let's write a message showing some information. So here we can see that we are getting the label from starting node label, and we are adding a message this node to that node has this distance. So if we have done our calculations correctly, then we would be able to get that information correctly. So let's save this, and now uh, let's try to visual see. So we would call the Dijkstra here, and we would pass graph. Then we would pass. We have now the function to find the source node by find node index. We would call this function, and we can call this by label. So let's say we want to get this starting node as A and the ending node as G. So let's try to find the shortest path between them. Let's see what it returns. So let's build this, and let's see if it is able to find that. And let me share my screen myself. So it is giving us 22 miles. So our Dijkstra is correctly implemented, as we saw in previous videos that the distance from A to G is 22 miles. But we also want to trace the path from A to which node we have traversed and how much distance it has and so on. So in order to traverse, we have to add something more. So let me quickly get back to code. So we also have to add something more to this code. So we would need another function which is called tracePath. So it would be another function. So this function would get some arguments and we would call it. So here, in order to get tracePath, we have to specify another variable called summary. So if it is in a summary mode, then we won't call tracePath, but if by default its value is true. So if it is not in summary mode, then we would call this tracePath. So here we can make sure that we are calling it. If not summary, if it is not in summary mode, then we would call trace. Okay, so let's try to pass some. This trace path would also have same arguments. So let's give those arguments very same arguments. So let's copy and paste them, and also add these arguments here. Now we can understand why we made a copy of the source node, because if we didn't make a copy, then when we are going to call trace path, we wouldn't have the correct source node. So that's why we made a copy. Now we would just pass graph source node index and destination node index. So what do we need from this function? We need this function to uh, trace back the path. We are getting the last node, as we can see that we have got this distance from the destination node index. In this destination node index, we also have get parent node index. So we would just try to jump from this parent to its other parent and so on till we get to the source node. So we would implement this here. So in C++, we have a very nice data structure called pair. So we would initialize our function by uh, vector of pairs, which we would call hops. So just like bunny hopping, we are going to hop from parent to parent and get to our source node. Then we would write a while loop, which would make sure that we are iterating over this whole array and vector, and we are getting back to our source. So here we are specifying a condition while destination node is not equal to source node. This is a terminating condition, and we are getting the parent node, parent index, and we also already have this destination index. So we make a pair such a way that parent index is the first element and destination node is the second element. Then we just make the current parent as the destination node index. So it would repetitively iterate and go back to the previous node and then the previous node and so on, and it would get its parent as well. So it would add this in hops vector. When we are done with this, we have a hops vector, but it's backwards. So the last element, which was the destination element, would be at the top and the source element would be at the bottom. So we have to just write a reverse for loop to actually trace back the path. So let's add that. So as we can see that this is a reverse for loop. It is starting from hop size and it is going towards 0 and I is decrementing. So we here we also find edge index because we need that information. So we would give detailed information on the nodes label, this node to this node via which route and what is the total travel time or what are the miles. So this trace path would complete our function. And if we want to run this again, so here we would also give the trace path summary as false in order to check our function if it's working correctly. So let's build this solution and let's run this, and let me share my screen with you. So once we run this, we can see that we have correctly traced our path as well. In order to get from A to G, we have to go to B, and its cost is two miles. Then we have to get from B to D, its cost is 5 miles, and then we have to get from B to G, its cost is 15 miles. So our Dijkstra is working correctly, and we have also managed to write the path tracing uh, as well. So let me get back to code. And now I would like to share a problem with you, a coding problem, and we would see why we have made this file like this. And I would also show you something else. So let me share the problem with you. So let me share this problem. Okay, so actually, I tricked you a little bit. It was a problem given to me by my friend some years ago, and we were to solve this problem. Here, this problem had a requirements, some requirements. Basically, it's a weighted graph, and we have to write a graph data structure that will compute the shortest path between two cities. And this was basically United States cities data, which we were given. And this file is cities called cities.txt. I will show this file to you as well. So in this file, we can see that they have specified the format, which is the same format that we have already solved for source city, destination city, route name, length of the segment. So we have to find this shortest path, and this is the format which we are already following. We have to give the source city, then the destination city and its summary. Okay, this is total distance of this much miles. Then we can also break down the distance from different hops. Okay, from this city to this city, we have this miles. Then we have to travel from this city to that city, and we have this much miles. So in total, when we add them up, then it would add up to this whole route. So this is basically it, and this they have also added this condition to provide a summary mode. If we are in summary mode, then we will only get the distance between source and destination, and if we are not in the summary mode, we would get this complete information. So we have already implemented that. So let me quickly go back to code, and let's now change the file to cities.txt. And let me quickly show you this cities.txt file as well. So here we can see that this is cities.text files. So here we can see that this is in quotes, and we have this route label, and then we have this route cost or distance in miles. So we have a very big file. It has a lot of edge data, and then it would also have a lot of nodes. But we have already done the hard work. We have done all this. And let me quickly get back to code, and let's test this out as well. So we are here, and just we don't need this anymore. I would just quickly add a system for inputting some values. So let me quickly add that. So here, here we are. Let me quickly go through this. First of all, when the initialization of graph is done, we need some visual confirmation. So we would just say, okay, we have initialized the graph. Now we would make this respective data structures, respective variables to capture the input. First one is source city name, then there is a destination city name, then there is a summary. So for summary mode. So here we also have to, because in our data structure, we don't have the search by label. We have actually the indexes, which we have to pass to the Dijkstra. So we have to make those indexes as well. Now, when we get input, we would just give a prompt, okay, enter the starting city name, then we would get this in source city name. And we are using getLine because the city name also has spaces in it. C in basically the scene has a limitation that it cannot accept spaces. If we add a space, then it would only pick the first word in a string. So we have to use getLine. So this is very simple. If we cannot find the city, then we would just exit and throwing error, and we would say that we didn't find any city. Then we do also see that destination city we couldn't find. If the similarly, if we couldn't find any destination city, we would throw that error. Otherwise, we have source city and destination city. Then we would be asked to provide if we want to have a summarized result or not. So we would just say yes or no, and based on that, we would call this the Dijkstra function appropriately. And that's it. So let's try to build this and run this. And let me share my screen with you as well. Okay, so let's provide the input which we know that we have the known result. So here in the starting city, we would say Manchester and why. I don't know the correct pronunciation, but I'm trying. So, and for the destination, we would provide Albany and why. So when we enter, we do want to summarize it. So first, for the first iteration, okay, let's go with the summarize result. And we see that we get this information, 2006 miles. Let's try to check this, cross-check with our Word file. And as we can see that in our Word file, this is indeed 206 miles. It means our Dijkstra is working correctly. Okay, let's try out another use case. So let's get back to its code, and let's run this program again. And let me share my screen with you, console screen. Okay, so let's provide these input parameters again. And this time we would say we don't want the summarized result. And here we can correctly see that we are getting the proper result. we are getting the distance, and we are getting the breakdown from which root to which root. So this matches with our Word file as well. And that's pretty much it. So this is how you implement the Dijkstra algorithm in code. And if you have any questions, please feel free to ask. And if you have any suggestions, please share them. Thanks for watching, and I'll see you next time.